Welcome back to TalkTensors.
Hello again.
If you are listening to this, you are probably the kind of person who counts parameters instead of sheep to fall asleep.
And your idea of a nightmare is a non-converging loss curve.
Exactly. We are the show for the gradient descent obsessed. We don't just read the abstract, we tear the paper apart, we check the math, and we try to see what really makes it tick.
That's the mission. We're always hunting for the signal and the noise.
And today, we're doing something a little different. We are setting the time machine back just a few years.
Just a few.
In the real world, that's nothing. In machine learning time.
Oh, that's the Paleolithic era. It's ancient history.
We are going back to the Wild West of, say, 2020 through early 2022.
I remember it well. I call it the era of the gigantic. Or maybe the era of irrational exuberance.
It really was an arms race, wasn't it? The prevailing wisdom was just etched in silicon. Bigger is always better.
It was.
If you wanted a smarter model, you just threw more layers at it. You stacked more attention heads. You bought more GPUs. It was this brute force mentality that just dominated all the headlines.
This is a very simple heuristic.
Yeah.
And you saw it play out. We saw GPT-3 land with that massive 175 billion parameter count.
Yeah.
It felt like an alien object had just landed in the field.
For sure.
Then, DeepMind responded with Gopher at 280 billion.
Right.
And then, not to be outdone, NVIDIA and Microsoft decided to flex with the Megatron Turing NLG, pushing it to a staggering 530 billion parameters.
It felt like we were building skyscrapers just to see who could touch the clouds without, checking if the foundation was actually solid.
That's a great analogy.
There was this unspoken assumption that intelligence was purely an emergent property of parameter count.
Yeah.
Like if you just made the brain big enough, it would eventually learn physics and poetry and Python code just by osmosis or something.
That's a perfect way to put it. But there was a massive overlooked variable in this whole equation. Everyone was so focused on the engine size, the dollars, the parameters, that they forgot about the fuel.
They forgot about the data.
Completely.
And that brings us to the paper we are deep diving into today. It is formally titled Training Compute Optimal Large Language Models, but the streets know it by the name of the model it produced, Chinchilla.
This paper is, in my opinion, the moment the music stopped.
Yeah.
It was the reality check the industry didn't know it needed, but desperately did.
It's a seminal text. The authors, Jordan Hoffman and the team at DeepMind, essentially stood up in a room full of people building these trillion parameter behemoths and said, you are all doing it wrong.
Very bold.
Yeah.
And very expensive to prove, which I'm sure we'll get into. But their core thesis was just earth-shattering in its simplicity. They argued that current large language models, the Gophers, the GPT-3s, were significantly undertrained.
Undertrained? That sounds so counterintuitive. I mean, GPT-3 was trained for months on massive clusters. How can something that expensive be undertrained?
It was undertrained relative to its capacity. The path to AGI, or at least to better performance, wasn't just about making the brain bigger.
It was about reading more books.
Exactly. It was about the ratio of compute to parameters to data.
Okay, so before we unpack how they proved this, because the methodology is just incredibly rigorous, we need to understand the old law.
Right.
We need to understand the rule book everyone was following before Chinchilla walked in and flipped the table.
Okay.
We have to talk about Kaplan.
Right. Kaplan et al., published by OpenAI in 2020. This was the governing document at the time. It's the scaling law Bible. If you were building an LLM in 2021, you had a printout of the Kaplan scaling laws on your desk.
So what did the book of Kaplan decree? What was the law?
Kaplan's analysis suggested that the parameter count was the dominant factor in performance. Specifically, they proposed a scaling ratio that heavily favored model size.
However,
the guidance was something like this. If you increase your compute budget by a factor of 10, you should increase your model size by 5.5x, but your training data by only 1.8x.
Wait, hold on. Let me process that. 5.5 to 1.8.
Yeah.
That is a massive skew. That essentially says, don't worry about finding more data, just make the model wider and deeper.
Precisely. It told researchers that data was a secondary concern. The widely accepted saturation point for data was thought to be very low.
So what did that lead to in practice?
Well, the standard practice kind of settled around 300 billion tokens of training data.
Just as a fixed number?
Pretty much. Whether you were training a 10 billion parameter model or a 500 billion parameter model, everyone just kind of stopped at 300 billion tokens. It was the accepted wisdom.
300 billion tokens seems like a lot to a human. That's a library of books. But for a model with 500 billion parameters, that feels like trying to learn a language by reading a single pamphlet.
That's it.
You have this massive brain, but you're just starving it of information.
Precisely. You ended up with what I call hollow models. Massive sparse giants that had the capacity to memorize the internet, but were only shown a relatively small snippet of it. They were, in effect, overfitting to a small data set relative to their size.
Okay, but we have to talk about the constraint here. This isn't just theoretical math, this is about money. We are dealing with compute budgets.
This is the crucial framing of the Chinchilla paper and what makes it so smart. In the real world, even at a place like DeepMind or Google, you do not have infinite compute. You have a budget, let's call it the dollars.
Right.
You have a specific number of FLOPs, floating point operations. Maybe you get a cluster of TPU v4s for 3 months. That is your budget. The goal then becomes to minimize the loss, the error rate within that fixed budget.
So the Chinchilla authors asked a different question than the Kaplan authors did. Kaplan asked, how does performance scale as we add compute?
Yeah.
Chinchilla asked, given we have this specific pile of money, or FLOPs, what is the optimal trade-off between model size and training data to get the lowest possible loss?
It's a subtle shift in the question, but it changes everything. It turns it into an optimization problem under constraints. And they didn't just guess the answer. They ran one of the most comprehensive empirical studies in the history of the field to figure it out.
I was looking at the appendix of this paper, and the sheer scale of the experiment is just mind-boggling. They trained over 400 separate language models.
400.
Yeah.
And these weren't toy models. They range from 70 million parameters up to over 16 billion parameters.
Oh.
And they train them on token counts ranging from 5 billion all the way up to 500 billion. They essentially grid searched the entire landscape of possible training configurations.
That is not a weekend project. That is a burn a few $1 million just to check the math kind of project.
It is, but that's the only way to be sure, right? And I love this because it shows real scientific rigor. They use 3 different angles of attack to prove their point.
3 different ways of looking at the same problem.
Exactly. And if 3 different mathematical approaches using different cuts of the data all point to the same answer, you know you've found something real. You know you found the truth.
Okay, so let's break these down because this is the real meat of the paper. Angle 1, fixing model size and varying tokens. How did this work?
So this is probably the most intuitive approach. Imagine you pick a specific model architecture, let's say a 1 billion parameter model. You lock that structure in.
Yeah.
Then you train it 4 separate times. Run A sees 5 billion tokens, run B sees 10 billion, run C sees 20 billion, and so on and so on.
So you are holding the brain size constant and just changing the amount of reading it does.
Exactly. And for each of these runs, you track the final training loss. But here's the technical nuance that is really important. They didn't just take the final data point from the loss curve.
Right.
They smoothed the training curves and interpolated them to find the minimum loss per FLOP.
Why the smoothing? Why not just take the final number? It seems simpler.
Because training curves are noisy. You know this. Sometimes a model has a bad batch or spike in variance, or the loss just jitters around near the end.
Okay, yeah.
If you just grab the final value, you might catch it on a bad step, an unlucky moment. By smoothing and interpolating, they constructed a continuous mapping from FLOP count to training loss. They basically drew a curve that represents the efficient frontier for that specific model size.
Got it. And when they did this for all the different model sizes, from the little 70 million parameter one up to the 16 billion one, what did the math tell them about the relationship between parameters and tokens?
It gave them a power law. And the exponents, let's call them Edom dollars for the 2 terms, were approximately 0.5 and 0.5.
0.5 and 0.5, so equal.
It implies equality, a 1-to-1 relationship. It suggests that if you double your compute budget, you should split that investment evenly. Double the parameters and double the data.
Which is already a huge departure from the Kaplan 5.5 versus 1.8 ratio. I mean, that's a massive correction right there.
A total reversal of the old wisdom.
Okay, let's look at angle 2, because this one gave us a very famous visual, the isoflop profiles.
This is my favorite approach because it visually demonstrates what I call the Goldilocks principle of machine learning.
The Goldilocks principle.
Yeah.
Not too big, not too small.
Exactly. Here, instead of fixing the model size, they fix the total compute budget. So let's say you have a budget of, 10, 20 FLOPs. That's your credit card limit. You can't spend more.
Okay.
You can spend that budget in a couple extreme ways.
Option A. You build a massive, massive model, but you can only afford to run it for a few training steps.
Right. Huge brain, no books.
And option B, you build a tiny, tiny model, but you train it on a mountain of data.
Tiny brain reads the entire Library of Congress 10 times over.
And presumably neither of those is optimal.
Exactly. So for each specific budget, they plotted the final loss against the model size. And when you look at that graph, you see a clear valley, a beautiful parabola.
So describe the shape for us. What are we looking at?
Imagine a U shape. On the far left side of the valley, you have the models that are too small. You're training them for trillions of tokens, but the model has saturated. It literally cannot store any more information.
It's full.
It's full. The loss is high because the model lacks capacity. It's under-parameterized.
And on the right side of the valley.
Other end of the...
On the right, you have the Kaplan models. They are huge, but because your budget is fixed, you ran out of money before they could converge. They are undertrained. The loss is high because the optimization process was cut short.
But at the very bottom of that valley,
the bottom is the sweet spot, the minimum loss, the optimal model size for that specific budget. And when they traced the bottom of these valleys across all the different budgets, from $10, $18 all the way to 10, 24 FLOPs, they found the exact same result as approach 1.
A straight line on the log-log plot.
A beautiful linear relationship. As your budget increases, the optimal model size and the optimal data size grow together perfectly in lockstep. Okay, so approach 1 and approach 2 agree perfectly, but they went for a third one, the parametric loss function. This one sounds a bit more intimidating.
It's the most theoretical of the three, but it's really beautiful. They tried to create a single mathematical formula, let's call it LARO and EUA, that could predict the final loss of a model based on just two numbers, the number of parameters, $9, and the amount of data, $1.
Let's try to unpack that equation. It has three terms, right? What is the first term?
The first term is just a constant, $. That stands for the irreducible loss. It represents the fundamental entropy of natural text.
Basically, language is inherently unpredictable. No model can ever have zero loss because sometimes I might say hello and mean goodbye, or I might use a slang word that didn't exist yesterday. There is always noise in the signal.
Exactly. Even a perfect God-tier model has a floor it cannot crash through. That's a yielder.
Okay, what's the second term?
The second term is essentially a constant dollar divided by dollars to some power alpha on the 11. This represents the error that comes from the model being finite.
So even a perfectly trained transformer with infinite data but a finite number of parameters still has limits. It can't memorize the entire universe.
Correct. As $, the number of parameters, gets bigger, this error term shrinks towards 0.
And the third term?
The third term is another constant, bar dollar divided by dollars to some power beta, plin BD beta. This is the non-convergence error. It represents the fact that we haven't seen infinite data. As the data set dollar gets bigger, this term shrinks.
So you have these two error terms in the equation fighting each other. One wants a huge $, the other wants a huge $.
And since compute, as we know, is roughly proportional to 6 times n times the you are optimizing this function under that constraint. When they solved for the minimum of this function, just pure calculus they found, well, you can probably guess what they found.
Let me guess. The exponents, alpha and beta, were equal.
Almost exactly. When they fit the data, they found that alpha was about 0.46 and the beta was about 0.54. Very, very close to 0.5 each. It confirmed the previous two findings with startling accuracy.
So we have three distinct methodologies: empirical curve smoothing, isoflop valley tracing, and theoretical loss modeling, all screaming that the Kaplan laws were wrong.
Completely wrong.
But why? I mean, Kaplan had smart people, they had data. How did they get such a different number?
This is the detective story part of the paper, and it's fascinating. It all comes down to a single hyperparameter, the learning rate schedule.
To learning rate. So the step size the model takes when it's updating its weights during gradient descent.
Right. Kaplan used a fixed learning rate schedule, but more importantly, they didn't adjust the decay horizon for longer training runs.
What does that mean, the decay horizon?
Well, when you train a model, you usually use something called cosine decay. You start with a high learning rate, and you slowly, smoothly lower it to 0 as you reach the end of your training tokens.
It's like landing a plane. You don't come in at full speed. You slow down to gently settle onto the runway or into the local minimum.
Exactly. But Kaplan was effectively training smaller models on more data, but they were using a learning rate schedule that was designed for a much shorter run. Or conversely, they were cutting the run short before the learning rate had decayed properly for the larger models. They were handicapping the smaller models that were trained for longer.
So they were running a marathon with a sprinter's pacing strategy.
That is a perfect analogy. Because they didn't adjust the cosine decay to match the longer token counts, the smaller models looked worse than they actually were. They appeared to saturate, but they hadn't. They just hadn't been given the chance to settle into the minimum because the learning rate was still too high.
That is such a subtle technical detail, but that one oversight skewed the entire curve and led to billions of dollars being poured into models that were just too big.
It implies that the curve Kaplan saw was actually an artifact of suboptimal hyperparameter tuning for some of their runs. Chinchilla corrected the schedule, making sure the cosine cycle always matched the token count. And suddenly, the smaller models started winning.
So let's state the new scaling law clearly. What is the final verdict?
The verdict is linear scaling. For every doubling of model size, you should also double the number of training tokens.
1-to-1.
1-to-1. Simple as that.
So if we use this new law and look back at Gopher, that 280 billion parameter monster, rest in peace, Gopher, ideally, for the budget they spent on that run, which was about $5.07 times 1023 FLOPs, what should they have built instead?
They shouldn't have built a 280 billion parameter model at all. To be compute optimal, they should have built a model with about 67 billion parameters.
That is tiny in comparison. That's a quarter of the size.
A quarter the size, but crucially, trained on 4 times the data.
And what about GPT-3?
Same story. 175 billion was way too big for the data it was trained on. It should have been much smaller and trained much longer to be optimal.
This brings up the 10 trillion parameter myth. I remember back in 2021, everyone was speculating, who's going to reach 10 trillion first. There were these wild rumors that GPT-4 is going to be 100 trillion parameters.
Right. And this paper essentially says you can do that, but unless you have a compute budget of 1024Ps, you're wasting your time and your money.
10 FLOPs. Just for context, Gopher used roughly 1024.
Yeah.
So we are talking about a budget 100 times larger than the biggest experiments of that era, just to justify a 1 trillion parameter model.
Exactly. A 1 trillion parameter model trained on today's standard data sets, say 300 billion or even 1 trillion tokens, would be severely, severely undertrained. It would be a hollow giant. It would be dumb for its size.
So the authors didn't just write down the math and drop the mic. They decided to prove it. They built Chinchilla.
The proof is in the pudding, as they say. They took the exact same compute budget that was used for Gopher. They said, okay, we have this amount of FLOPs. Let's spin it at the Chinchilla way, the optimal way.
So instead of 280 billion parameter.
They built a 70 billion parameter model.
And instead of the standard 300 billion tokens.
They fed it 1.4 trillion tokens.
Okay, let's look at the specs here. 70B params. 1.4 T tokens. They use a data set they called massive text. We need to talk about data quality because 1.4 trillion tokens is a lot of reading. What's in massive text?
It's a carefully curated mix. You have the standard C4 data set, which is a massive web crawl. You have Wikipedia, naturally. You have huge corpus of books, both fiction and nonfiction. You have GitHub code.
And they weighted these subsets, right?
Yes, and this is key. They weighted them very carefully. They didn't just dump them all into one big bucket.
You don't want 90% Reddit comments and 1% Shakespeare.
Right, you get a very interesting but probably not very useful model. They upsampled the high-quality data like books and Wikipedia. But the key here is just the sheer scale. 1.4 trillion tokens was unprecedented for a single epoch training run at that time.
And they made some architectural tweaks too, right? It wasn't just a parameter change.
Minor but important. They switched from the standard Atom optimizer to Atom W.
Why does that matter? For our listeners who aren't deep in the weeds on optimizers.
Well, Atom W handles weight decay better. In the standard Atom optimizer, weight decay is coupled to the gradient update, which can get a little messy and sometimes doesn't regularize as effectively as you think. Atom W decouples it.
Okay.
This typically leads to better generalization and lower final training loss. It essentially helps the model settle into a more robust minimum. It's a small change that makes a real difference at scale.
They also tweaked the tokenizer using sentence piece without NFKC normalization. That sounds like jargon soup. Can you explain that in simple terms?
Yeah, so NFKC normalization is a text standardizing process. It turns fancy characters into standard ones. For example, it might turn a specific mathematical symbol for integral into just a plain letter I or something generic, or collapse different kinds of quotes into one.
Which is really bad if you are trying to learn math or chemistry or even code.
Exactly. By removing that normalization, it helps with representing math, chemistry formulas, and code much better. It keeps the raw symbols intact. It allows the model to see the real texture of the data.
Okay, so they built this sleek, dense, well-read model. It's smaller, it's been trained 4 times longer, and it has a better optimizer and a better tokenizer. How did it do?
It crushed everything.
Everything.
Virtually everything. Chinchilla uniformly outperformed Gopher, GPT-3, Jurassic 1, and even the massive 530B Megatron Turing model on almost every downstream task they tested.
Let's talk about MMLU, massive multitask language understanding. This is basically the SATs for AI. It's the gold standard benchmark.
It's a very tough benchmark. 57 different subjects, everything from elementary math to professional law, medicine, and psychology. Gopher, the previous champion, scored a respectable 60.0%.
It's not bad. A passing grade is usually 60 in school, right?
Sure, but Chinchilla scored 67.5%.
That is a 7.5% absolute jump. In this field where people fight tooth and nail for 5% improvements, that is a generational leap.
It is. I mean, to put it in perspective, Chinchilla beat the expert forecast for where AI would be the following year. It was effectively living in the future. It accelerated the timeline of AI progress by 12 months in a single paper.
Wow. And on specific subtasks within MMLU.
It scored over 90% on sociology, U.S. foreign policy, and international law.
So it's a better diplomat than Gopher was.
Significantly better. And on the Big Bench benchmark, which is a collection of diverse, specifically hard tasks designed to break LLMs, Chinchilla improved over Gopher by an average of 10.7%.
What about common sense reasoning? Can it answer simple questions?
They tested it on natural questions, a closed book QA data set. And the closed book part is important. It means the model can't look up the answer. It has to know it from training.
Right, it has to be in its parameters.
Exactly. Chinchilla hit a new state-of-the-art, 31.5% accuracy on 5-shot. Gopher was sitting way back at 21%.
That's a 50% relative improvement. That is staggering.
It is. And remember, I have to keep emphasizing this. Chinchilla is 4 times smaller.
That is the so what factor here. It's not just that it's smarter, it's smaller.
This is huge for production. Think about inference cost. When you query a model, you have to load those parameters into memory, into VRAM. A 280B model like Gopher requires a massive cluster of GPUs just to serve one request. It's incredibly unwieldy and expensive.
It's like firing up a jet engine just to toast a piece of bread.
That's it, exactly. Chinchilla is 70B. It fits on much smaller hardware. It runs faster. It uses less energy per token generated.
So if you are a company deploying this, say, Google or OpenAI Chinchilla is infinitely more valuable than Gopher, not just because it's smarter, but because it doesn't bankrupt you to run it.
It changes the economics of LLMs completely.
Right.
It shifted the focus from training cost to inference cost. The authors realized that while training is a huge one-time cost, your CapEx, inference is forever, your OpEx.
Right.
A smaller, better trained model pays dividends every single time someone uses it for years to come.
And fine-tuning, too. If I want to take a model and fine-tune it on my company's medical records or something.
Downstream tuning is so much easier on a 70B model. It's more nimble. You can iterate faster. It's cheaper. It just democratizes the ability to specialize these models.
However, it's not all sunshine and rainbows. The paper does dive into the ethical considerations and limitations. The authors were very honest about this. Did being compute optimal fix the inherent problems of LLMs, like bias?
Unfortunately, no, not at all. They tested it on winogender, which is a benchmark specifically for gender bias in pronoun resolution.
This is the test where you have sentences like, the doctor called the nurse because she was late, and the model has to figure out who she refers to.
Right. And historically, models will default to stereotypes, assuming the doctor is male and the nurse is female.
So what did Chinchilla do?
Well, Chinchilla was better at resolving the grammar. It correctly identified the pronouns more often than Gopher did, but, and this is the important part, it still exhibited significant bias. It was much better at the female not gotcha examples, the stereotypical roles, than the male gotcha examples where the roles are reversed.
So it's a more competent model, but it's just competently reflecting the bias of the training data.
Exactly. Better language modeling does not equal better sociological reasoning. It just means it emulates the source text more accurately. And if the source text is biased, which, let's be honest, the internet is, the model becomes a higher fidelity mirror of that bias.
And what about toxicity? Did it become less toxic?
Same story. They ran it through real toxicity prompts. There was a negligible difference between Chinchilla and Gopher. Improving the loss function did not reduce the generated toxicity.
This brings us to the data bottleneck. The authors explicitly flag this in the conclusion of the paper.
They do. And this is perhaps the most forward-looking part of the paper. They state clearly that if we follow this new scaling law, we're going to need larger and, more importantly, high-quality data sets.
You can't just scrape the garbage bin of the internet anymore.
No. If the scaling law says we need 1.4 trillion or 5 trillion or 20 trillion tokens to justify the next generation of models, where does that text come from? We are rapidly running out of high-quality human text.
We've read all the books, we've scraped all of Wikipedia, we've read all the code on GitHub. What's left?
The paper implies that the next big frontier isn't model engineering, it's data curation. The cleaning of data, the creation of synthetic data, that is the new gold rush. We can't just feed the beast more, we have to feed it better.
It's a fascinating pivot from build a bigger engine to refine a better fuel.
And that is the true legacy of Chinchilla. It stopped the blind race for parameters and started the intelligent race for data efficiency, data quality, and synthetic data generation.
Okay, we've covered the history, the math, the model, and the fallout. Now it's time to get a little speculative.
My favorite part of the show.
Welcome to Novel Notions.
And the disclaimer. The following ideas are for entertainment and intellectual stimulation only. Please do not bet your PhD thesis on our late-night ramblings.
Although if you do, and it works, you have to name it after us, or at least send us a t-shirt.
A t-shirt would be nice.
Okay, idea number 1. I'm calling this the data compute recursion loop.
Ooh, recursive. I like it. Tell me more.
So the paper proves data is the bottleneck. We're running out of good text. But we just discussed that Chinchilla is statistically better at identifying high information density than simple heuristics or classifiers. It knows what good text looks like because it has lower loss on it.
Okay, I think I see where you're going with this. You want to use the model as the judge of quality.
Exactly. What if we use Chinchilla, let's call it Model A, to read the entire messy, noisy, unindexed web? All the stuff we usually throw away because it's too hard to clean with simple reject scripts. We task Model A with filtering and curating that mess.
You use the compute optimal model as the filter. It reads a paragraph and asks, does this look like high-quality training data to me? Does this have low perplexity?
Yes. Model A creates a new hyper-quality data set distilled from the noise. Then we take that new data set and train Model B, same size, same compute budget, on the synthetic curated data.
And the mechanism here relies on the idea that loss is fundamentally tied to token quality. So if Model A can identify tokens that lower entropy more efficiently than our crude filters can, then Model B should achieve an even lower loss per FLOP than Model A did.
And then Model B becomes the filter for Model C.
It's a breeding program for textbooks. You are essentially distilling the internet through a recursive loop of increasingly literate models. Each generation creates a better curriculum for the next.
Exactly. Breaking the running out of internet wall by mining the bad internet for the gold that our simple scripts are currently missing.
You know, it's very plausible. The paper shows that data quality matters immensely. If you can automate quality detection at scale, you might unlock a whole new scaling law. We are already seeing the beginnings of this with things like constitutional AI and synthetic data pipelines today. It's a great idea.
Okay, idea number 2, I'll call this one dynamic morphology, or the breathing transformer.
Sounds very biological. I'm intrigued.
The paper assumes a fixed parameter count, $, for the whole training run. You start with 70B, you end with 70B. But approach 2, the isoflop analysis, showed us those distinct valleys of optimality.
Right. For every given budget, there is an optimal size. The valley moves.
But what if $' wasn't a constant? What if we started the training run with a massive, sparse model, say 500 billion parameters, a huge sponge? It has low data density, but it has this enormous capacity to absorb diversity early in the training when the gradients are large and messy.
Okay, so you capture the broad strokes of the data distribution with a massive net. You learn the high-level structure of language very quickly.
Exactly. But then, as the token count accumulates and we move further along in the training run, the model prunes itself in real time. It distills itself down, following the Chinchilla optimal curve during the training run.
So instead of minimizing DN, where $, is fixed from the start, you treat $, as a function of time $. You're trying to traverse the valley floor as you train.
Yes. You start high up on the left of the graph, and you slide down that curve to the bottom right as training progresses.
So you would end up with a 70B parameter model at the end, but it would have the wisdom of a 500B parameter start.
Precisely. It learned the big picture with a big brain, and then it solidified the fine-grained details as it shrank. It's like how the human brain prunes synapses as we grow up. We start with more connections than we need, and we prune them down to become efficient.
That is a fascinating idea. It effectively decouples the exploration phase of training from the consolidation phase. The math in the Chinchilla paper actually suggests this could work because the optimal model size is dynamic relative to the compute spent so far. If you could implement a dynamic architecture, which is incredibly hard engineering-wise, it could theoretically beat the static Chinchilla law.
We'll let the listeners code that one up for their next project. If you figure out how to dynamically resize a transformer without the gradients exploding, let us know.
You'll probably win a Turing Award if you do.
That wraps up our deep dive into the Chinchilla paper, a paper that told us all to stop buying more GPUs and start reading more books.
Quality over quantity, efficiency over ego.
It's a lesson that still resonates so strongly today as we move into the era of models like Llama and Mistral, which are very much the spiritual successors of Chinchilla.
Absolutely. The era of the hollow giant is over. The era of the dense scholar is here to stay.
As always, the link to the paper is in the description. Go read the graphs, especially those isoflop valleys. They are genuinely beautiful to look at.
And check out the MMLU breakdown. It's humbling to see a model answer questions about international law better than most lawyers.
Until next time, keep your learning rates scheduled and your gradients flowing.